So, we continue to discuss the lectures on topic advanced marine structures, lectures on module 1. In the last lecture we discussed about basically two theorems which are used for doing plastic analysis of sections. One is what we call as the static theorem, other is the kinematic theorem. Both theorems should yield me the same collapse load, though the procedure may be different. So, the main difference between the two theorems which we saw yesterday was, in this case you must know the statically admissible and safe bending moment distribution, whereas in this case you got to assume a mechanism, and for that mechanism you will always compute the collapse load or the true collapse load. So, this theorem gives you values which will be lower than that of the true collapse load, whereas this theorem gives you the values which will be either greater or equal to the true collapse load. So, we call this as upper bound and we call this as lower bound. So, the moment we understand that kinematic theorem needs me to assume a mechanism or static theorem needs me to do a safe bending moment distribution. So, for the structure to remain statically indeterminate of a very high order, I must know what are the possible mechanisms I will get in a given structural system, or I must know how to do the bending moment distribution for a structure which is statically indeterminate of a very high order. So, both ways it requires a prelude or a precondition that one must know the classical structural mechanics to do a plastic analysis. Okay. So, plastic analysis can be seen as an advanced method of analysis with respect to the elastic convention analysis. So, if you do not know elastic analysis, you cannot proceed with the plastic analysis, because both at least one method demands you to find out the bending moment distribution for this. So, let us focus on this term mechanism. We already said mechanism is a structural system which cannot offer resistance to the external load applied to it. So, obviously a given structural system assembly of members will have a certain resistance to the forces. So, we cannot say it is a system where it does not offer resistance. So, we correct our statement saying that it is a structural system which cannot offer resistance or does not prefer to offer resistance to a load beyond certain value. That value is what we are trying to capture, that is what we call as a collapse load. So, the term adjective collapse may cause a confusion to people, saying that is this method really leading towards a collapse mechanism or collapse of the structure. It is not so. We have already seen in the last lecture that my load factor accounts for enough margin of safety which is comparatively or reasonably better or similar to what we have in a conventional working stress design and elastic analysis. Okay. So, talk about mechanism, there are different kinds of mechanisms available which we must understand. So, I can divide this globally into two. One is what we call as an independent mechanism, other is what is called as combined mechanism. Suppose I have a beam which is simply supported, subjected to a point load, central concentrated load, where the spans on either side are equal, then there will be only one hinge formed here. These two will be structural hinges. I think you now understand how I am drawing the plastic hinges and structural hinges. Why I am drawing one hinge? Because this is static degree of indeterminacy for this beam is 0, is it not? It is determinate structure. So, I need only one plastic hinge to make it as a mechanism. This mechanism is what we call as beam mechanism. Suppose you have a structure which is a frame let us say ABCD subjected to a central concentrated load on the column, let us say the span being equal. I can also draw a similar mechanism to the column like this. There can be a hinge, there cannot be a hinge here, that we are not bothered. So, this is also still called as a beam mechanism only. Okay. Some literature address this as column mechanism, but it is one and the same, right, and so on. I have a frame, similar frame subjected to a lateral load, let us say W. The frame will have a tendency to sway. Okay. This frame has static degree of indeterminacy of how much? 2. Okay. It has got 2 degree of indeterminacy. So, I need 3 hinges. Or if you consider the axial deformation also, I require consider the axial deformation also, then it will be 3, therefore I require 4 hinges. So, hinges can be formed here, here, here and here. This mechanism is what we call as a sway mechanism or panel mechanism. If you look at a gable frame, then there can be a mechanism like this. This is what we call as gable mechanism. All these are examples of independent mechanism. If you want to look at an example of a combined mechanism, let us say I have a frame subjected to a lateral load and a gravity load. So, hinge may be formed here, here, here and here, and this is 90 degree, there is no hinge formation here. This is what we call as a combined mechanism. You may wonder why it is called as a combined mechanism. I will explain you. This mechanism has 2 things inbuilt into it. One is a beam mechanism similar to what you have here, other is a sway mechanism similar to what you have here. So, I can combine this. Okay. Now, what do we do by identifying independent mechanisms? For every independent mechanisms available in the structural system, you must try to find out the possible collapse load. Okay. Since I am assuming the mechanisms and trying to find out the collapse loads, each one format of the problem will give me one set of collapse loads. Okay. And since I am following the kinematic theorem, because I am assuming the mechanisms, I will get collapse load for each one of the problems separately independently, maybe independent mechanism, maybe combined mechanism, all will be aligned and I must pick up the lowest value. Why? Because as far as the kinematic theorem is concerned, for an assumed mechanism you will always find the collapse load either greater or equal to the true collapse load, is it not? Is it not? So let us say I get WC1, WC2, WC3, 3 collapse loads from 3 independent mechanisms. For example, from a beam mechanism I get WC1, from column mechanism I get WC2, from combined mechanism I get WC3. Okay, I must compare all these things and pick up the lowest value, because WC1, 2, 3 at the best will be either equal to collapse load or greater than the collapse load, is it not? Therefore, I pick up the lowest. So do not get confused that upper bound theorem means pick up the highest, lower bound theorem means pick up the lowest. It is not like that. While picking up the value, it is controversial, right, because these values will give you in true sense more than the actual value or worst by worst equal. So WC1, WC2, WC3 either all will be equal or all can be greater than the true collapse load. So I must pick up the lowest one. Okay, so do not get confused with upper bound means highest value, lower bound means lowest value, it is not like that. Okay, be very careful with the statement. Now let us see what are the steps involved before we do couple of problems today. What are the steps involved in both the methods independently? So very simple, in this method a structure is given to you, loading system is given to you. In this also structure is given to you, loading system is given to you. Plastic analysis is not a technique which will help you to choose a structural form. Okay, structural form is chosen for marine structures depending upon what is the functional requirements, where water depth is to be provided, what is the other kinds of loads coming onto the structure, what is the deck area required, all these are covered in what we call as feed. Okay, that is called front end engineering design. So we do this and check the layout of the platform, select a platform or select a form, geometric form, structural form of the platform. So for all practical purposes, to do a plastic analysis, the structural form and the load coming on to the structure are available to me. All these loads have variabilities, uncertainties, these are all called working loads. Okay, I multiply this with a factor, make them as factored loads, then apply them to the structure. Okay. So the steps involved in this case is, having given both the theorems require a structural system and the set of forces or loads coming onto the system, in this case draw the bending moment diagram for external forces and redundant forces. What do you mean by external force and redundant forces? External force are applied forces, redundant force are support reactions of the structure. We must draw bending moment diagram for both. Then choose the maximum ordinates of BMD, check whether it is sufficient to form a mechanism. What do you mean by a mechanism here? So I am having a bending moment diagram, I pick up the points in the bending moment diagram which is having the maximum ordinates. Okay. Let us say the degree of indeterminacy for my problem is 5. How much plastic hinges should I get to make it as a mechanism? 6. So I must get number of plastic hinges required is 6. So it means plastic hinges will generally form at sections where the bending moment is maximum. So I must at least select 6 sections. I must at least select 6 sections where the bending moment is maximum in the given system. So it forms a mechanism. Okay. Then find the collapse load and choose the true collapse load. How will you choose the true collapse load? If you have got different mechanisms, different possibility combinations, okay, you must select them and each one of them will give you different load sets. They will be lower than or worst to worst equal to the true collapse load, you must pick up the maximum value. Okay. Let us say in this case how do we do? For a given system, assume a mechanism. And for an assumed mechanism, apply principle of virtual work to compute the collapse loads for each assumed mechanisms. So, for each assumed mechanisms you will get one set of collapse loads, all of them either will be greater or at least equal to the true collapse load. So, choose the true collapse load. So, let us put a very clear statement here. If you got many mechanisms, choose the lowest WC, okay, choose the lowest WC. Any doubt here? So, there is one more theorem which we call as uniqueness theorem. We will discuss that quickly and then take up few examples on beams and frames and try to do plastic analysis and find the collapse loads, then it will be clear for you how we are estimating them. Uniqueness theorem states that for a given structural system and loads acting on it, there exists a safe and statically admissible bending moment distribution, then for the bending moment distribution indicating satisfactory number of cross sections with higher bending moments, which are nothing but sections of possible plastic hinges. The corresponding load will be equal to true collapse load. It will be neither higher nor lower, it will be exactly equal to the collapse load. This theorem is also called as combined theorem. The name combined theorem is given to this theorem because of one reason, that it is combining both the principles of static and kinematic theorems. It combines static theorem because it requires admissible bending moment distribution, it combines kinematic theorem because it is checking whether the sections develop enough number of plastic hinges to make it as a mechanism. Okay. So, it is combining both, that is why it is called combined theorem, and this theorem can be plotted like this. If we talk about curvature and WC, WC will be keep on dipping and the curvature will be keep on increasing, and in another case WC will be keep on increasing. So, one is upper bound and other is lower bound, or one is kinematic, other is static. Can you tell me which is kinematic, white or green, and why? So, this will be kinematic, because in this case W will be either greater than or equal to WC. And of course, this will be static. In this case W will be either less than or equal to WC, and uniqueness theorem is this horizontal line. This is uniqueness theorem where W will be equal to WC. Is that clear? Now, we have been talking about mechanisms, we studied independent mechanism, we understood combined mechanism. All these mechanisms will enable n number of plastic hinges to form, so the structure does not reflect or react back to the applied loads. Okay. There is something called partial collapse, complete collapse, over complete collapse. If R is the degree of indeterminacy, I am talking about static degree of indeterminacy. If the number of plastic hinges formed are less than or plus 1, then it is called partial collapse. If the number of plastic hinges formed are equal to r plus 1, it is called complete collapse. If the number of plastic hinges formed are more than r plus 1, this is called over complete collapse. This generally occurs in symmetric structures or structures with symmetric loading. Okay. Where plastic hinges do not lie along the axis of symmetry. So, not necessarily always you require r plus 1 to make it as a mechanism, okay. Can I have less than r plus 1, still it is called as a partial collapse. Can I have r plus 1 more than that, still it is called as an over complete collapse, okay. So, r plus 1 is a strategy to understand the structure will become a mechanism, but even if you have plastic hinges less than r plus 1, still it will collapse partially, okay. Let us take some examples now and try to understand both the theorems by solving these examples. I will take simple problems first, then I will slightly take complicated problems later in this lecture, so we can demonstrate this. So, I will take example 1, we will take a simply supported beam. The simply supported beam subject to the central concentrated load W, span of the beam is L. We all know the degree of indeterminacy of this beam is 0, it is determinate structure. So, how many plastic hinges are required to make it as a mechanism? 1. So, number of plastic hinges required to make it as a mechanism is r plus 1, that is 1. Where plastic hinges can form? It can form at the following locations: 1 under the concentrated loads, 2 at supports which are fixed, at sections where the bending moment is maximum, and so on, is it not? This is what we have seen yesterday also. So, these are 2 supports where there are structural hinges already available. So, plastic hinges cannot form here because bending moment is 0 at these points, okay. So, the only point available in this beam where plastic hinge can form to make it as a mechanism is the point C. We can call this A, B, C, okay. So, let us first solve this problem by static method. So, static method says I must draw the bending moment diagram, is it not? Let me draw the bending moment diagram for this. 0, 0 at the supports and this value. What is this value going to be? WL by 4. That is the bending moment diagram ordinate here, okay. And I understand that there will be a hinge formed here and this value will become MP directly, is it not? So, let me write down the value here, static theorem. So, MP will be equal to WL by 4 or WC will be 4 MP by L. I am writing directly collapse load because there is only one possible bending moment distribution I can do. If I got few more, then I could pick up the values and compare them and find out the highest of this and wrote WC, but there is only one possible distribution I have, therefore I wrote WC directly. Is that okay? Then let me draw the plastic hinge formation. So, this is the original line where the beam is rest. Now, this is going to be my deformation or deformed shape of the structure. There will be structural hinges here and there is going to be a plastic hinge here, is it not, right. So, I call this deflection as delta and this rotation as theta. Because of symmetry, this will also be theta. You can agree that this tangent will have 2 theta rotation, is it not? Agreed? So, principle of virtual work has to be applied for kinematic theorem. What is principle of virtual work? What is the external virtual work? External virtual work is the load multiplied by deformation, which is W into delta, okay. What is the internal virtual work? Internal virtual work is the work done by the hinge. We already told you yesterday, plastic hinge is a hinge which requires a moment to rotate, it will not rotate freely, is it not? What is that moment required to rotate plastic hinge? MP. So, it is going to be MP multiplied by 2 theta, that is the work done. Now theta and delta can be compared from the geometry. I can simply say tan theta or theta is directly delta by L by 2, if this is L and this is L by 2. So I can say simply it is 2 delta by L. Is that clear? So let me compare this. So I should say, let me write down here because it is very difficult to focus. I will write down here. So I should say W delta is MP, theta I am replacing as 2 delta by L. Okay, delta goes away. I can straight away say WC is 4 MP by L. Is that okay? I get the same answer as I have here. So both the theorems will give me the same value. Okay. Any confusion in this example? I start with a very simple example just to understand, because bending moment diagram for a simply supported beam is what we all know. Okay. Any doubt? Let us do one more example. Let us take up an example where the loading is eccentric. I have a simply supported beam again, but the loading is not equal. This is A and this is B, and of course this is L and this is W. Okay. So the degree of indeterminacy for this beam is 0. Number of plastic hinges required for this section to make mechanism is 1, and where it will form? It will form under the concentrated load. Okay. I call this A, B and C. The possible location of the plastic hinge is at C. That is a possible location. So let me draw the bending moment diagram for this. So this is going to be a bending moment diagram. What is the value here? WAB by L. And I know that this is going to be the section where the bending moment is maximum. So this will be a location where plastic hinge can form, which make it as a mechanism. So let us do the static solution for this from static theorem. I know MP is simply WAB by L. So WC is MP L by A. Let us solve this problem using kinematic theorem. I have a structural hinge here, I have a structural hinge here, there will be a plastic hinge here. Okay. I call this as delta, this as theta 1 and this as theta 2 now, and the rotation total will be actually theta 1 plus theta 2. External virtual work is equal to internal virtual work. External virtual work is W into delta. Internal virtual work is nothing but MP of theta 1 plus theta 2. Is that okay? Now from the figure, theta 1 is delta by A or delta is equal to A theta 1. Also from the figure, theta 2 is delta by B, that is delta is equal to B theta 2. So theta 1 can be expressed in forms of theta 2 because they are equal. So if I say, I will remove it here. A theta 1 can be B theta 2, therefore theta 1 can be B by A of theta 2. Okay. So, let me get back here. So, W delta is going to be equal to MP of theta 1, which is B by A of theta 2 plus theta 2, which is MP A plus B by A of theta 2, which is MP L by A of theta 2. Let us remove this also. Theta 2 can be said as delta by B. Okay. So, W delta is MP L by A, theta 2 is replaced as delta by B. So, delta goes away. So, WC is MP L by AB, which is the same as I have here. Okay. Let us do one more example. This time we will take a fixed beam. I will take a fixed beam with central concentrated load, span of the beam is L. Now, what is the degree of indeterminacy of this beam? Okay, how will you calculate degree of indeterminacy? There are three kinds of supports we have in general. One is what we call as an hinged support, roller and fixed. The three supports, how are they marked? Fixed is marked like this, roller is marked like this, and hinged is marked like this. Okay. Fixed will offer three reactions, one vertical, one horizontal and one moment. Roller will offer only one reaction, which is vertical. Hinge will offer two reactions, one is vertical and horizontal. Okay. Now, let us ignore the axial deformation present in the system, therefore, all horizontal reactions we will ignore for the time being. If you ignore that, obviously the modified reactions for this could be only vertical, for this could be only vertical, for this could be vertical and moment, right. Let us use these values here to understand. So, this got 1, 2, 3, 4, 4 unknowns. Okay. How many equations equilibrium I have? There are 4 unknowns which are reactions. I am neglecting the axial deformation. So, 2 equations I have, sigma Fy 0, sigma m 0. These are 2 set of static equations of equilibrium which I can apply here. Therefore, degree of indeterminacy, which I call as 4 minus 2, which is 2. So, the R value for this problem is 2. Agreed? So, R is 2, therefore, the number of plastic hinges required will be 3 to make it as a mechanism. So, where they can form, what are the possible locations where these can be formed? They can form now in all the 3 points A, B and C. A and B because they are supports, fixed supports, C because it is a point of concentrated load. Okay. To make it as a mechanism, let us solve this problem first using static. So, I would like to draw the bending moment diagram for this first. There are 2 bending moment diagrams for this, one is because of the load, other is because of the support moments. Okay. Because of the load, the value is going to be, how much is value? This central concentrated load is going to be WL by 4. Okay. Now, I have the support moments also. From your knowledge of understanding, can you tell me what are the support moments a fixed beam will develop because of a central concentrated load here, it is going to be WL by 8. Okay. So, I plot this here. This is WL by 8 and this is negative and this is positive, okay, because this is because of the external load, this is because of the internal reaction. They will have bending moment at the bottom maximum, but these two will have bending moment at the top maximum. Okay. So, negative moments and positive moments. Now, I want to superimpose them. What I do is, with respect to this line, I flop this, I just rotate this. If I rotate, it will become like this. Agreed. Why this has gone up? Because this WL by 4, this is half of that. So, now this value what you see here is WL by 4. Agreed, I have just flopped this, that is all. Okay. So, the plastic hinge which you are interested is, one will form at the support, one will form at the section, is it not? So, this will also be MP and this will also be MP, the net moment. Okay. So, I should say now 2 MP is equal to WL by 4, 2 MP is equal to WL by 4. So, therefore, I can say WC is 8 MP by L, is it not? Let us do this problem by kinematic theorem. Are you following or not? If you do not follow, please stop me and ask. As I told you, plastic analysis requires certain basic understanding of static indeterminate structure solution. Okay. So, unfortunately, in this course we will not discuss about the how to solve the static indeterminate structures for analysis, elastic analysis, how to get the bending moment diagram and all. Okay. This is something which you must know, but still I am trying to explain to the maximum possible within the given span of time. Okay. So, now I am trying to do a mechanism here. The mechanism is well understood that there will be a hinge here, there will be a hinge here and there will be a hinge here. This is going to be my deflected profile of the beam. So, this is delta, this is theta, this is also theta. So, this is 2 theta. Agreed. Now, let us see what is the external virtual work. Nothing but W into delta, okay, W into delta. Internal virtual work has happened in 4 places, 1, 2, 3 and 4, all are MPs, is it not? So, MP times of theta, 2 theta and theta, is that okay? That is 4 MP theta. Agreed. I can now connect delta and theta by a simple relation. I will do it here, I will remove this. So, from the figure, okay, this is L by 2. So, W into delta is 4 MP times of 2 delta by L. So, I should say WC is 8 MP by L, which is as same as what you get here. I can solve these problems by both the methods using both the theorems, I will get the same answer. Okay. So far in all these problems of examples, there was only one possible mechanism which can directly give me the WC value, is it not? Suppose if I have more mechanisms, I must select the higher or the lower depending upon the method I am using. We will do those examples also possibly in the next lecture. Okay. Thank you.